Yeah, sorry, I didn't change the schedule. We're a bit uncertain. Okay. So we continue our discussion on the Monge Ampere equation. So we have learned about classical solvability. Okay. And now let me state a result, which is one of the very fundamental regularity results for the Monge Ampere equation. Okay. So now we know that Monge Ampere equations in general, you cannot expect the same regularity, interior regularity that you have for the Laplace. Right, at least in dimension higher than 3, higher than or equal to 3. We have seen various examples, right? Kovalorov kind of example and so on. Okay. So now the thing is that therefore to run the theory, what you typically need is what I was telling, is that you take a supporting plane, and if you are able to lift the graph, that is at this point P, so this direction is say P, so what you do is, or you lift the graph, okay? So that it cuts the section. And so this section is what, so you lift the graph at height h. This is the domain, and this could be my section. Okay, so this I will call as my SH, which will also depend on T and the point. Let this point be x0, then generally it would depend on x0 and T. Okay, and now so this is defined as 1, where so this is a set of all y such that u of y is below this tangent plane. Okay, which is less than or equal to u of x plus p y minus x plus h. Okay, and this is a convex set because u is convex. Okay, so this is a convex set, and now the theory is that if SH, which will be the final theory, if SH is compactly contained in omega, then u is strictly convex. And C1 alpha. So I start with that of u equals to f, which is like comparable to 1. Okay. So in the case where you don't assume anything on f, it is C1 alpha. Okay. So strict convexity, this is something I would quantify that would give me C1 alpha. And the second part of the theory is that if f is C alpha, then u is C2 alpha. So these are roughly the two results that would be done by us. So the key insight that Luis Caffarelli had was that, and that Roberto also mentioned, and I also mentioned in the other talks, okay, where what you do is that this SH is convex. So I can use a transformation that moves into a piece like this, such that, and after an affine transformation, there is ball of radius 1 here, and such that n times the ball or whatever c times the ball contains it. Okay, so over here, the solution roughly looks like this after the transformation. Okay, if I normalize it in the right way. So Caffarelli, so from this picture, you go to this picture, provided you cut a section which does not see the boundary values. Okay, you go to this picture. And this is a normalized picture, and then what I will show is that in this normalized picture, if at all I can start this process, I will have a universal strict convexity character which will be uniform across a family of solutions, which will give me a uniform C1 alpha estimate, which will involve a lot of different convexity kind of arguments. And subsequently, if I know that my right hand side is close to 1 at a certain rate, that would be further upgraded to C2 alpha. Okay. So this would roughly, so this was the key insights that Caffarelli brought in here. So if you want to prove a certain property there, you come here, you prove everything, and then you go back and forth. Okay. So this is the key insight. So in order to do so, you at least have to know that you can start the process somewhere, which you cannot do for these Kovalorov kind of solutions, because if you try to do and you try to live this section, you always hit the boundary, right? So you cannot do the process over there. Okay. So now first I will mention, which is one of the very fundamental estimates for Monge Ampere, which is the Kovalorov estimate, that if you have a strictly convex solution which will be quantified a certain way, then u is indeed smooth. Okay. So Kovalorov. So it is done in more generality in the same case, but I will just take that of d square equals to 1. Okay, in omega, and u equals to 0 on the boundary of omega. Then what you have is that you have a control on d square u from above at a point which depends on the distance of x from del omega, grad u, and so on. Okay, this is the Kovalorov estimate. Clear? And where the right hand side is 1. So therefore, I mean, this is a situation where you have been able to cut a section, so you are in a normalized situation, and here you have this estimate like this. In this situation, you have an interior estimate. But this is a situation that you cannot do for this example again. Let me remind you again. Because when you try to cut the section, this section doesn't stop till it reaches the boundary, right? And at the boundary points, I don't have any control. So essentially, I don't have any compactly supported section in there, so I cannot do this normalization. So this is one significant estimate, okay, that I would do. So let me defer the proof of this for a moment, okay? And this is something that I would come back to at a later point, okay? So this is the Pogorelow's classical estimate in the 1960s. So what is Luis Caffarelli's theory? It is about if you have a less smooth right-hand side, whether you can get high regularity. And that is particularly relevant because if I just give you the prescribed Gaussian curvature equation, which is f of u, supposing f of x, u, and even the normal vector, you don't have this, okay? F depends on x and this normal vector, which is 1 plus that goes to the other side. At the first step, if you know that f at the first step, because of convexity, you know that gradu has a bound, right? And therefore, you know that f is bounded from above and below. If you choose your f rightly, right? I mean, if you solve a given, so this exactly f of x times 1 plus gradu square whole to the n plus 2 by 2, right? This is how you solve the problem. So f is good, and if the gradu is bounded, then this is a nice quantity. So then the Caffarelli's estimate, the one that I have, will give me u is in C1 alpha. Because this is the point where I cannot start Pogorelov, right? I need something intermediate. Once you have C1 alpha, this will upgrade to C alpha, and this will give me that u is C2 alpha, and then I can keep bootstrapping, and then I can keep enhancing the regularity depending on how much my f allows. Okay. So therefore, this is the context where the theory applies. Okay. So this is the Pogorelov estimate, and now I start the process. Okay. As I said, I will assume that I have a situation where I'm able to cut a section so that I have a section which is compactly contained in the domain and does not get as close to the boundary. Okay. So this is my situation, and then what I do is that I normalize it. So normalize means, so you have this section, and this is my domain far away, and then I use a transformation, or maybe the other way around, AH, okay, to this section. So AH is a mapping from Bn, means NB, to whichever region, such that An of B1 is trapped inside SH. Okay, so you use this mapping to trap this. Okay, which so because you know that any convex set you can trap an ellipsoid, right? So inside this convex set that is over there, I will have that there is an ellipsoid such that n times the ellipsoid is contained here. And now what I do is that I use a transformation, an affine transformation that makes this a ball. Clear? What is the John's ellipsoid lemma that I described? That if I have this section, if I take the largest ellipsoid that is contained here, okay, then n times the ellipsoid traps this section, right? And if I use my affine transformation, okay, which will be now in this case AH inverse, this would be my AH, that would normalize it, okay? I would not know where the values go, but so I should, in principle, this is my H inverse, but I will come back because finally I will deal with a domain which is like a ball. So therefore, I will use AH for this direction, okay? So there is an AH inverse, okay? I'm purposely telling that makes it a ball, okay? So that in the change picture, I have that this is how the zero set would look like, okay? And there is a ball inside, and such that n times the ball contains this. So this is the ball 1, and this is the ball n. And this is my section S of H tilde. So what is this S of H tilde? I use the affine invariance, right? So what I have is that because it is AH, so U tilde equals to det of which way is AH? Okay, so det of so what I do is that, so I have something U tilde, so U tilde has to be defined a certain way. So U tilde of x equals to U of, I move the point here, from x I go here, which is AH of x, and then I have to multiply by the right conformal factor, which sort of preserves the structure, right? So this is my U tilde of x, and this is now defined in a domain which is the following, right? So this is like this region, there is a ball inside, and n times the ball contains it, okay? And now in this picture, how does my solution look like? And I know that so this makes it like let me call this, give this a name, let me call this S1. Okay, well, I should not call it S1 to begin with, but eventually I will call it S1 once I know how these values change. Okay, at this point, let me call it omega. So therefore, for u tilde, I have that u tilde satisfies det of b square u tilde equals to f of ax, which is my f tilde, which I will keep calling as f of x, okay, in omega, and omega is trapped between Bn or Nb and contains B1 and u equals to 0 because at the boundary of the section, u is 0 on the boundary, u tilde. Okay, so from now on, this will be my u. The one that I call, because I have cut a section, I'm well inside, and now I can start the process. At least for some h that I have, I can start this. Of course, you may say that the C2 alpha has to depend on h. Of course, it will, because you can have many such possibilities, right? Because you do not expect that the ellipse and the ball will have the same d square u, even though the det of d square u is roughly the same, right? So at some h when you cut, from then h onwards, the C2 alpha estimates have a universal character. That is the key point of this theory. Okay, so this will be my u tilde. Okay, I will keep calling it u. Is it okay? So now the first thing, so this is my domain omega, and here what I have is that u is. So let me first keep it as it is. Okay, and so therefore what I know is that the minimum of u tilde, okay, which is h tilde, is what? This is equal to det of AH minus 2 by n of minimum of u, okay, minimum of u minus this affine function, okay, and this is in size equal to 8, right? Because I lift this tangent plane at a height 8, so I know that the minimum value, because when I did not lift it, it was the supporting value for u of x naught. So I started at a point x naught, okay? Suppose this x naught is such that I have been able to include a section in, okay? So this minimum value has now become h tilde. So h tilde is comparable to det of AH whole to the minus n by 2, right? Agree? Times h. Otherwise, everything is 1. So the theory is too good to be true. So now what I do is that I should show a bunch of things, okay? The first thing that I show is that, what thing first? The first thing being h tilde is comparable to 1. So this essentially was covered by Devobrotto. So suppose I have this, okay? And now suppose this is the value of h tilde, okay? Now what I do is that I know that this is there, this is a ball, and this is contained in n times the ball. So at this ball, I draw this paraboloid, which is like of the type 1 by 2 mod x square minus 1, make it 0. So after this, it exceeds 0 before it reaches. So this is B1, this is omega, and this is Bn or Nb. Well, Bn is also the ball of radius n, right? So I think it's fine. So it is somewhere, okay? So it need not be at the centered at the minimum value, but it is somewhere, so, okay? Because a ball one can be located somewhere. Because the section that I cut can very well be like this, right? And this is something I have to rule out, and where I will sort of imitate some of the arguments that were earlier discussed in brief, because at this point I really don't need to trap the curvature, I just need to trap the height. So what does it say? H tilde is comparable to 1. This is just telling you that det of AH minus n by 2 times h is comparable to 1. So that means that det of AH is comparable to h to the n by 2. This is a key thing. That it could be that in some directions, so the ellipse that you trap in the original picture, in this picture, this ellipse could have bad eccentricity. That is, some axis could be very large, some axis could be very small, but the volume should still behave like h to the n by 2. Okay? And it is the eccentricity of this ellipse that will finally give information at smaller and smaller scales about d square u, right? Because if I give you a paraboloid or a ball, right? So then if I have 1 by 2 mod x square minus 1, if I trap a section at h, this ball roughly looks like square root of h, maybe up to a factor, right? And all the side, all the directions, it looks the same. But instead, if I have, say, in 2 dimensions, something like delta of x square plus 1 by delta of y square, you clearly see that what we have done is that in the y direction, over here, in the y direction over here, we have tried to sort of made the curvatures sort of very large, okay? And in the x, you have sort of made the curvatures very small, right? So we have stretched the x by 1 by delta so that the curvatures fall like delta, while in the y, we have sort of squeezed in so that the curvature becomes very large like delta. Okay, delta or the square root of delta. Okay. So this is one thing. Well, it exactly behaves like delta. Okay. So the stretching is like square root of delta, and the whole behavior of the curvature then becomes like delta. Okay. So you see that. So the eccentricity of the ellipse would finally give me the information about d square. And I want to say that if I can start the process, then at smaller and smaller section, I can sort of get a good control on the eccentricity, and that will upgrade my information from a C1 information to a C2 information, and then I can go to C2 alpha, right? So this is one thing, and the other thing is that the distance of h, the distance of the minimum point, so h tilde. So this is again the picture, and I want to say that I want to get a hold of, so this size is like 1. So this is in true sense. That's why from now on, I will call it instead of omega S1, because it's almost normalized to 1, right? But now the problem is that at the point of the minimum, which is say a point here, over here, and this is say the unit ball, and this could be my minimum point, right? I want to say that at x naught, d of x naught from del omega is like comparable to 1. Okay? That is, it's not too close to the boundary. And as Debabrata said, one thing is that what I do is that I join it by a cone. And at least I would know that there is one segment that connects this point to this minimum point, right? And suppose this distance is d. Let's call this distance d, right? Suppose this distance is d, then at least I know that there is a supporting plane, okay? There is a supporting plane with a vector which is decided by this cone, which is of the size. So there is a vector rho in, so this, let's call it in, so let's call this Cx, and this is my u, okay? This is my u tilde, which I will, after this step, I will keep calling it u. But till this step, at least I need to know that h tilde is comparable to 1, which is telling me that this map has volume which is like n by 2, h to the n by 2, which is like telling me that this ellipse and this ellipse has volume like h to the power n by 2. But now I also want to know that the point where the minimum is attained is not too close to the boundary in the normalized picture, which is not yet normalized. After this, it is a legitimate normalized picture. Okay. So x naught, so this is d. So there is a vector in grad u tilde of x naught such that the size of rho is comparable to 1 by d. Because along this, I mean, there is a supporting plane, at least there is 1. On the other hand, if I take the diameter of this domain, which is like 1, and this value is like 1, okay, there exists a ball of 1 which is contained in, so first let me put everything for Cx, okay, Cx of x naught. But then there is a ball 1, okay, which is contained in grad of Cx of x naught. Because the whole diameter, okay, and if I take a slope like in ABP, okay, then I have to hit it somewhere, because if I follow this, otherwise I can never reach the minimum point, which is at a distance 1. This is 0, this is at level -1, so I can never reach this. And if it is a supporting plane somewhere, and it is a cone centered at this point, so it is also a supporting plane for this x naught, right? Yes? So this is there. And I know that because the picture is like this, okay, the picture is like this, any supporting plane for this is also a plane of support for this u tilde, right? Because I have to cross this. They have the same boundary values, right? So therefore, I also have the information that del u tilde of d1 of this picture omega traps, what is it called? Traps del Cx at x naught in full measure, which is the corner, okay, of this cone. And now what I need to do is that I need to, let me go to another picture. Well, I don't want to, because the first part is done, so h tilde is comparable to 1. And because if I go to the other picture, I would not have any control of sort of what exactly has been written. So let's get a hold of this Cx tilde, Cx at x naught, okay, which is the minimum point where I join. Now you have to see that this is the image of this or this number of such supporting planes. This is a convex set, right? That's not very difficult to show. And then it contains one vector rho in rho in Sn minus rho in Rn is there in this what is it called? So that rho is in grad of Cx, C of x naught. Okay, at x naught. So let's call this cone C of x naught for C of x naught. Okay, let's call this. And moreover, this also contains a size of B1. Maybe not B1, B1 by 2, B1 by 10 million, but at least of the order 1. So therefore, and I know that this is a convex set. So what I do is that I take the ball of 1, and it is these too close, so 1 by d will be very far. So I take where, so there is a plane, so there is this vector rho, there is the ball of size 1, okay, in the support, among the supporting plane. So therefore, there is a plane of orthogonality, right? So there is a plane wave which is normal to this vector. So you take this plane. And these are all points in the support of this. And because it's a convex set, so I can take this cone. So this cone is also in the support of this. And this cone has size, this is size 1, and this is size 1 by rho. Right? And so therefore, the total size of grad of C of x naught or grad of C x naught is bigger than equal to 1 by rho. But on the other hand, because this is included in grad of u of omega, and because I have a control on the Monge Ampere measure, so I know that my delta of d square u is like comparable to 1. This is less than equal to the measure of omega. So that quantifies my rho, right? Because that tells me that my rho cannot be that small because 1 by rho is less than equal to this. So therefore, this point, in a very universal way, cannot be too close to the boundary. Okay? Is it clear to everybody what exactly is going on? I'm sort of working only on the support plane. Okay? On the support, I have one vector, which is the vector where you have the maximum slope, right, which is closest to the boundary. On the other hand, I also know that I have all these other slopes, right, which is decided by the diameter of this region divided by the height 1, because the cone does not go below height 1. And then I know that I will have a lower dimensional surface, okay, n minus 1 ball, which is where all the vectors are orthogonal to this rho vector. And then this whole entire cone has to be in the support, because this is a convex set. And this has size 1, this has size this, and therefore the whole size is whatever it is. Okay, but if you sort of look at this estimate carefully, if I do it for a general picture, this will be like diameter raised to the power n minus 1, and this will be the distance from the boundary, right? So for a general UX, this also gives me, which I will make as a side remark, the Alexandrov maximum principle, right? The Alexandrov estimate. Because this is also something that I will be needing. That if you have delta of d square of u equals to some f is what is like 1. Okay, I'm not trying to quantify, and u is equal to 0 on the boundary, then u of x, if I don't do it at a minimum point, is less than equal to first the distance from the boundary, and then the diameter raised to the power n minus 1. The other thing to note is that for the, I erased it. So yes, I did. So if you remember this argument, I had this and I had this. Okay, to get a control on this h tilde, the ball that I had, this could exceed the domain, right? This is not a problem. So even if the section is not compactly supported, my sections can the volume of the sections can be upper bounded by h to the n by 2. It's only for the other bound that I have an issue. Clear? Because this would give me a bound on h tilde, at least from below, which will translate into a bound on that of the AH from above because of this inverse relation, right? So therefore, even if, so this is another small comment, even if SH in my original picture, before I normalize the picture, is not supported in is not compactly supported. Okay, then SH has to grow at like h to the n by 2. Okay, this is another information to know. And what does the Alexandrov estimate tell you? U is 0, right? So therefore, this is 0. So to drop to half or if you scale it to 1, drop to half, at least you have to move by a fixed amount from the boundary. And this is the quantified information, which is also quantified in that very normalized picture where I've put all the diameter like 1. Okay, but I don't want to repeat this estimate again and again. So it's good to write it in the general one, right? Because if I have a general domain D with diameter, the number of supporting planes that I have will be at least include a ball of the diameter, right? Size of the diameter. And then in addition to that, because of the cone that is above it, okay, with the same boundary values, I would also have at least one vector of a size which is 1 over the distance. If I put all of that together, the support will include a cone where one of the vertical axis would be of the size 1 over the distance, and the base would be of the diameter, which is like the diameter of the domain. So that is n minus 1, which is what reflects in the diameter, and the distance to the omega. So a lot of information all embedded in one. Okay. So this is the Alexandrov's estimate. Kovalov's estimate. Okay, so this also has to end. I mean, I know this is very heavy, but I mean, it is what it is. So now, after all of this, I am in a normalized situation. Okay. So what does it tell you? So now it tells me that this picture that is too close to the boundary is a fake picture, right? So this cannot happen because I have a uniform control on x naught from the boundary, right? Because I have a bound on this row from above, right? Or 1 by rho from below. So therefore, the actual picture has to look. So this will be a ball. It was earlier centered somewhere else, and this is my point x naught of minimum, and this is the end ball. And so therefore, because this is the point which is say situated here, so this is my domain. So this is the point x naught, and this is the unit ball. So that n times the ball contains here. At least over here, I know because it's sort of far away from the boundary. At least there is a C-size ball, universal, which is contained in. And if I go to my original picture, which is the picture that I started with, that just tells me that when I cut this section like this is the minimum point. So let me sort of draw it somewhere else. If I cut my section like this, minimum point, and so I move it over here, and so I sort of put it here. So this is like a bigger domain, right? And this is the region of the section, okay? Well, let me erase this because this is unneeded. And so, because it's an affine transformation, and I know that earlier I knew that there was an ellipse here, but the affine transformation, either it changes all directions the same way, right? Because it's after an affine transformation, and on this normalized picture, I know that this ball and this ball are comparable. So that a large C times the ball contains this Bn, right? Clear? This ball and this ball are comparable. So therefore, what it tells me that I can enclose at the point of minimum, I can center the ellipse here. I will lose the constant n, which I don't care, so that I will have an ellipse EH of x naught, which is contained inside SH. Okay, this section at x naught, such that this is contained in some large C times EH of x naught. And moreover, in this change picture, this has size 1, this has size 1, and because the determinant of AH is a size hn by 2, h to the n by 2, so this ellipse, all these ellipses of x naught that I can do is of the size hn by 2. So that just tells you that if you cut a section at a point, the section is kind of balanced around that point. You can so earlier this ball could have been situated somewhere else, like in the picture over there, but now I can center the ball there. Okay, and when I come back, I get this ellipse which behaves the way as the picture shows. Okay, so even if you have slept, at least the pictures are there. So this will give you a good account of whatever that happened. No, I'm just joking. Okay, so. ठीक है. So what else? So now I will show the property that this brother was mentioning, which then will imply the strict convexity. Okay, that is the dichotomy. Okay, so far what do we have? If I have this curve, even if it can have a corner here, if I can cut a section somewhere, okay, then at least I can start the theory. Okay. And now, so therefore, these are typically, if I round it off just for exaggeration, these are going to, so at the points of strict convexity means that you can slice it by planes so that in the limit, it is just that point. Okay. Yeah. Or said differently, at that point, you can sort of have a supporting plane which only contains that point, and all other points sort of curve up. So these points of strict convexity, morally you expect are the regular points, right? And so I want to understand the set when the strict convexity fails. Okay, clear? So I want to understand. So I want to understand the set of singularities of this. So I have let of b square u like 1. Set of singularities. Let's call this set S. Okay. So I want to see that if U matches an affine function, where does the support of that of the coincidence set lies? Okay. So what I'll do is that I will subtract off that affine function, make it 0. So a very general situation that I have is that of b square u is like 1, u is non-negative, and the plane is 0. Xn equals to 0. So I will assume that u is equal to 0. That's that. So suppose I say that. So the contention is that u equals to 0 cannot have interior extremal points, right? So this should be written in principle above this. So suppose I am assuming that 0 is such an extremal point, okay? So in general, the thing is that you cannot match on an affine plane on an affine function which has such that the coincidence set has an interior extremal point. So if at all, so in this picture, what I would want to have is that at least in this situation, not the picture is not yet drawn, I would want to know that the support of U has to exceed the domain, which was the case 3 in Devobrato's case, right? In a situation. So what do I do? I'm just trying to find the board where I can maximize the picture for an exaggeration. So let me pick up this code. The color at least. So let me sort of draw an exaggerated picture. So suppose I know that there is a segment, at least there is a segment which ends at 0, where u is 0. So I have a situation where det of b square u equals to 1, u 0, 0, and u is bigger than or equal to 0. That automatically means that xn equals to 0 is a tangent plane, right? Okay. So I have this ball. So, and what I'm assuming is that the surface lifts up at 0. And moreover, what I have is that for this support, so the 0 set is contained in the set after a change of coordinates xn less than or equal to 0. Because this has to happen because there has to be at least some plane, because this set is convex, right? So there is a supporting plane to the 0 set. Okay. So this is like over here. So okay, so this is my plane. So at least I know that this has a delta segment. Okay. So suppose there is a delta segment. So so this is the direction of En. Okay. So this is of size delta. And now what he did is that you cannot take this as a tangent plane. You shift backwards up to the size delta and you tilt it up. Tilt up the tangent plane. So what you do is that you take an L. So this is a bad picture. So let me try to. Okay, so this is the one. So this is the picture. So this is the one. Okay, so this is the direction En. This is the size delta. And what I do is that in that delta, I tilt the tangent plane. Okay, and this will enclose. So what I do is that I take L to be epsilon times, I move back, and then so this will in principle enclose cut a section, right? So this is 0, and this will sort of cut this section, right? So this was my 0 set, and this will cut this section, right? This plane will cut this section. Clear? So this is the plane that I tilt, and the slope of the tilting is epsilon, and I center it at delta, right? So this is some delta point, 0, 0, 0 delta, which is included in the segment, and I put it like epsilon xn plus delta, right? So it will slice the graph, and suppose this is the slice region, okay? So up to this region are the regions in the plane which lies below that section. It is not really a section at 0, but it's morally a section. Why? Because at this point 0, because there is a delta segment, the difference between u minus L at 0 is like minus epsilon delta. And because the slope is delta and the size of the region is 1, so the minimum can, and u is bigger than equal to 0 otherwise, the minimum can at most be like minus 1. And this delta is fixed. So that means that the minimum of u minus L at 0 is comparable to the total minimum of u minus L in this section which is below, right? Clear? So u minus L at 0 is comparable to the minimum, and that theory that I did not only applies to a minimum point, it applies to all points that is close to the minimum. So all these balancing of sections that I did, they all apply at points where it is close comparable to the minimum, right? Because I never quantitatively use the fact that it has to be strictly the minimum, right? Okay, so that means what? So at this picture, if I look at it, so this is my region, okay, this is my region, and this is the, if I put it down, and this purple region is my other region, right? So this is the region where this pink region, this side, is the one where u is less than L, the tangent plane, and L epsilon. And now because independent of epsilon, because this is also, sorry, this is comparable to minus epsilon, I'm very sorry. This is the key part, not minus 1, minus epsilon, because this is of size epsilon, it will slice the domain has size 1, right? So it cannot be more than minus epsilon, right? And this is minus epsilon delta. I mean, somebody should have told me. This is minus epsilon, this is minus epsilon delta. So, but delta is like, it's like given to you, right? There is at least a segment of size delta that where it ends at an extremal point, which is 0 for this, okay, for this affine plane, which I have normalized to 0. So therefore, this is the situation that I have. And so because u of L minus 0 is comparable to the minimum, because the order is delta and delta is like order 1. So therefore, I should be able to, thanks to my balancing of section property, I should be able to find an ellipse such that large 3 times ellipse has to trap this region. Okay? But now as I let epsilon go to, and this ellipse and this ellipse has to have at least one axis which is comparable to delta, right? Because this delta segment has to be trapped inside, right? Because these are all part of the, because this whole delta segment is a part of the region for every epsilon, which is below the plane, right? All this delta segment. So that means that if I take this ellipse, so let me draw another picture. If I draw another picture over here, so I have this region where the zeros lie, and at least this is a delta size region where the zeros happen, and this is the pink region, okay, which is a function of epsilon. So this is corresponding to L epsilon. So let me call it PL epsilon, where u is below the L epsilon, okay. So if I'm able to trap an ellipse, because then u minus L0, this is almost the minimum, this is like a section. So this ellipse and large 3 times ellipse independent of epsilon has to trap this region. So that means that this along this axis, this largest ellipse has to have an order delta. It means that along this axis, the smallest ellipse also has to have order delta. But if I make epsilon go to 0, this pink region goes to this boundary point. And so therefore at this point, this will contradict the uniform balancing of at 0 of u minus L. Right? This will contradict the uniform balancing, because as epsilon goes to 0, this pink region goes to this. Right? Because then it becomes L equals to 0, and I'm assuming that 0 is a extremal point, right? Where u matches 0. So therefore, this cannot be. Okay? So therefore, what I am saying is that if at all u matches a line, it has to exhaust the domain. Okay? So let me try to quantify this information. Is the proof clear? Because every time, because this minimum is this is the minimum of the global minimum, and they are like comparable to one another. So it means that I can balance my section at 0, independent of epsilon, because this ratio is independent of epsilon. That is the key thing. But then when I try doing this, I get that because there is a delta segment inside, again I'm repeating the argument. So the largest ellipse as well as the smallest ellipse on this side has to have a size at least delta. But that cannot be, because as I make this epsilon go to 0, this pink region goes closer and closer to 0. Okay, and that contradicts balancing of u minus L epsilon for say small enough epsilon, right? So now, so that means, that tells me that if u is equal to L on a line, okay, if u is equal to L on a line, then that coincidence set has to reach the boundary. It cannot stop at an extremal point that is inside. And so that means that, so that is almost like strict convexity, okay? But then when I try to quantify this strict convexity, this will take me to the C1 alpha. So now I will get C1 alpha. It will tell me that if I have a normalized solution, okay, I will use this result to show that if I have a normalized solution, C1 alpha estimate, universal C1 alpha estimate or normalized U. What is the normalized U? That is, at some point I could cut the section. I'm trying to remind so that I get to here, which is now very well normalized because H tilde was comparable to 1. Solution, I have that delta of d square U is like 1, okay, and the minimum of U and U equals to 0 on S1, because S1 means that omega which is cut, and S1 is contained in Bn, and S1 is contained in a large C, large B of large R by C, and it contains B1, okay, because now I can center the section at 0, right? Clear? So this is the normalized solution that I have, and I will quantify this into a C1 alpha estimate. So suppose, so this is my situation, okay, and I know that the minimum is far inside, so I will draw a nice picture now, okay, and then what I do is that I cut this with a cone. So this is my S1. If I project it down, if I project this picture down, this is my S1, and I cut it at half. So suppose this is the half point. So this is S1. That is when I cut the section at size 1. So you move this to 0. Earlier it was at -1. You move it to 0, and I cut this section at 1. Okay. This I can do because H tilde is comparable to 1, so I divide it by a constant which makes it 1. Okay. I cut it at this. Now I look at it at half. So this is the cone, right? So what this is telling me is that the surface has to curve up. Okay. So there has to be so at half. Okay. If I take half, what is this region? This is simply this. If I project down, is like 1/2 S1, right? Because this is where it matches the cone. Okay. And now what I want to say is that the surface has to curve up. So the S1/2 will be a larger region, which is this. So the S1/2, if I project it, should be this. This should be S1/2 when I cut the section. Okay. And now my claim is the following. And now my claim is the following, that my claim is that there exists a universal delta bigger than 0, such that because there is a separation, I want to say that there is a universal delta for which this happens. There exists a universal delta bigger than 0, such that 1/2 plus delta of S1 is contained in S half, and this is contained in 1 minus delta of S1. Now this part is easy. Well, nothing is easy, but what I mean to say is that if from S1, if you have to step down to half, or if you can push the graph down, you step from 0 to half, right? The boundary value is at 0. But then you have to go away from the boundary by a fixed chunk. So this inclusion is Alexandrov maximum principle, right? You have to move away from the boundary by a fixed chunk so that you can drop from 1 to half. And about this part is where I will use the compactness of this family of normalized solution. Okay. So now suppose I assume that, so for this I really need to quantify the information. And this I do by Caffarelli's compactness, which is to say that, so suppose let me draw this picture again. And suppose the surface is like this, and this is the cone. Okay. And so this is the cone. And this is the bigger region. that if this distance goes to 0, I cannot, suppose I say I cannot find the universal delta. That means that for every, if I take delta equals to 1 by k, I can find the UK such that along one direction, this distance is like less than equal to 1 by k. That means that I can find the delta such that I have this normalized picture and these UKs, so maybe U1 gets 1 close along a different direction, U2 gets 1 by 2 close along a different direction, U3 gets 1 by 3 close, and so on. But then this is the normalized family, right? Because I have a bound on the boundary and these are convex functions, so I get an uniform Lipschitz estimate inside. So UK converges locally something, right? At least in all this region. So, and the Monge Ampere measures also converge. So delta of d square UK are all comparable to 1, so they converge, right? That is not the problem, right? Because they are all bounded. So if UKs converge, the Monge Ampere measure also converges. Okay. Now the thing is that, but these directions can rotate a lot. But again, I can find a subsequence of these directions which converge because Sn minus 1 is compact. The set of all directions is compact. So I can find that. So therefore, at least I can find a picture like this, that I can have this. So along a certain subsequence, I can assume that they sort of get. Let me sort of prove this. Okay, so along a certain sequence of directions, so what I have is that this converges to this line, right? Along a sequence, so therefore what may happen is that, so I take these UKs, they converge to U0, so that this distance closes along some rate, along some line, right? So therefore, along that rate, for this U0 limit, what I will have is that I will have a picture like this. So this could be like this, and then this is a cone, and this is a cone. So this becomes the cone over here at 0, and this curves up in the other side. So along a certain plane cross section, I will have this line, right? Because as these curvatures go to 0, okay, from below, they converge to this along a certain subset of directions, right? Along a subset of sequence, because up to a subsequence, these EKs also converge to some E0, right? And the limiting one becomes the supporting, becomes the place where which is the coincidence set for the limiting U0, right? So this will be a picture like this for the limiting U0. Okay, just one second. And so therefore, now I see that this violates the no segment result, because now I have a ray where U matches an affine function, and this ray originates from 0, which is an interior extremal point, and then this ray comes down. So therefore, what it tells you is that this distance has to be universally quantified. So whatever is true for one function ends up being true for the entire family by compactness, because the family of normalized solutions are compact. Because otherwise, if this gap reduces a bit from one side or the other, then up to a subsequence, I can find the limiting one where this gap narrows to 0. So along this it narrows, but on the other hand, it can possibly still curve up, just to be optimist. So then I will have a section which may look like this. And that cannot happen, because then along this line, it has an extremal interior point at 0. Because whatever I did for U equals to 0 is also true for U minus L, where L is this line. And so this is a rate that originates from 0, and that is bad for me, right? So therefore, it cannot happen that this gets too close to each other, because otherwise by compactness, I violate the no segment result for the limiting function. Okay? So this tells me that there is a delta that works for this. So this is more quantified by Alexandrov, right, in an explicit way, but this one is more indirect. And this is the kind of the brilliance of Luis Caffarelli, right? I mean, whatever it is. So yes, now.
Just asking a silly question, like, can't we go in one direction? Why do we take all the directions? You're going through all the directions, right?
No. I'm just telling that for each of these UKs, there is a possible EK along one where it gets 1 by k close along some okay. But then the thing is that, so these directions can rotate. But then I know, because of the compactness of Sn minus 1, along a certain subsequence k going to 0, these EKs converge to E0. And then you use the compactness of this normalized family to know that this E0 then becomes the corresponding ray or the direction for where U0 matches this L0. And that cannot be, because if you go here and below this, it goes here. So therefore, U minus L only matches up to here. And I know that this whole graph has to curve up. So this has to be then for the limiting one, for the limiting picture, which is over here, this becomes U minus L naught, which is corresponding to E naught. This becomes the extremal point. And that violates the fact that if there are singularities, that has to exceed the domain. So therefore, I have this. So now let me even say something more. So this is just C1 alpha. This is nothing more. And once I have C1 alpha at a point, by the semi-continuity property of the differential that Debabrata mentioned, I will get that the slopes cannot increase too much in a neighborhood, because otherwise it has to cross the domain. Okay? And we know that for convex functions, the local supporting planes are the global ones.
Limit. So you is the sequence which converges to
Yes.
naught, and so at each point, so the modulus of convexity is like decreasing.
Yes, along some of the lines which we don't know.
Right. So at least you will find a point which will converge to this line.
Yes.
Where the
Exactly.
But I mean, how can I make sure that this is the interior? I mean,
Well, interior, because this is a 0. So I don't know. It could sort of say exceed here, but at least I know that this has to end at 0. Because below this, the curve goes up, but this goes down. So at least 0 is an extremal point. This side I don't care.
the way I see it, that I mean, it is affine, right? So here it is 0, it matches. So where the limiting function?
So limiting function along a certain direction, along a certain plane projection looks like this.
Yeah, exactly. No, I mean, the point where it violates. I mean, so this one you are using. So at some point x naught, where it will violate the modulus of continuity, right? So I mean, the limiting function u naught.
Yes. So it violates the no segment result.
Yeah, that is fine, but I'm trying to understand at which direction. So
along this limiting direction, so at least along one direction, because when I say that this round curve gets close to this cone which is also round, it means that there exists a certain direction where this closeness is realized, right? It is possible that in other directions it's still far away.
I mean, the condition is violated, so you will find at least one point xk, say. Now xk will converge to some x naught.
Yes.
And now how can I make sure that x naught is lies within the interior of that segment? So is that something?
No. What I'm trying to say is that okay, no. So that is not a problem, right? Because this plane is below, because that is convexity, right? This curve is below. So when I go here, I have to match on the entire line. I don't have a choice. If I match here and I match here, then I have to match on this entire strip by convexity.
That is fine.
And so therefore, on this strip I match, this can exceed the domain, fine, but this has to end here. So at least I have on the coincidence set of u naught minus L naught, there exists the interior point of the interior extremal point, which is this origin.
It matches at these points. So at
Yes, and then it has to match everywhere in between.
The limiting function, they will have to match at the interior point. Then only you can say that it is fine along the line, right? So
yes, it matches at the interior point, which is origin.
Minimum point every limiting function. Every UK
Yes, exactly.
At 0.
Yes.
Okay, maybe I'll ask the question later.
Okay, that is fine. So you see what I'm trying to say. So let me draw the one-dimensional picture to convince more. So what I have is that along a line, what I can do is that, so suppose this is the one. So this is kind of curving. And along this it is good. Okay, along a subsequence of direction. So when I sort of match, as it gets close to this, it has to match somewhere here. Okay, but then by convexity, it has to match on the entire line.
No.
And this line has a ray which originates from 0, because below this the curve is above and this ray goes below. So 0 is an interior extremal point.
That is fine, but my question is a little bit different. Maybe I'll ask you later. Okay.
But is it okay that this gives me a delta?
Yeah, I mean the argument is fine. Okay, so I'm just trying to understand. I mean, why the limiting function? You see, I mean, at 0 and at this point, it has to match with this line, right? But the limiting function, so you will find at least one point where it should match, right?
Match the line, yes.
Exactly. And then only you can say that it
yes. So it matches the line at s1/2, which is far away from 0, because it is at 1/2. So this is located far away. So I know that when it matches, this point is not 0.
Okay.
Now I understood your question. So from half to 0, you have to have a good separation. And at half where it matches, it's a distinct point. And then by convexity, you can match everywhere. So that's what I was referring to. So wherever you do, it has to match here. And then by convexity also. Okay. So that is what you were also telling?
No.
Okay. So anyway, so I get that there is a uniform delta. So now let me sort of draw this picture again. So I have this, and now I will draw a better picture because I know a lot more. And I have this cone, and I cut it at half, and then I know that at this point I can, well, this is bizarre. I will draw it like a ball, and I have this cone, and I'm assuming that u of 0 is 0 and u is bigger than or equal to 0. So this is a supporting plane. And what this tells you that as soon as you can cut a section, okay, and that eventually, once you prove the regularity results, which is the C1 alpha estimate, becomes your tangent plane, which is what you eventually want to establish. Because for a convex function which is C1, you have that, I mean, that is the unique one, right? So then what happens? That here is a gap, right? So therefore, at the next level, when I cut it at half, I can increase this cone. Right? I can increase this cone. So therefore, and now if I slice it at half and half and half, this cone of monotonicity increases. So at every step, what I am doing is that I get that u, the value of u in, suppose u of 0 equals to 0 and u is bigger than or equal to 0 and delta of d square u is like 1. I know that u in half f1 is less than or equal to, by this delta, 1 minus delta, or call it delta tilde, which is decided by the delta times half, which is the value at this cone, right? And then if I repeat this process, S1 is like normalized, comparable to 1, I can repeat this. It is a good point. I think it clarified that point. So it is a good point. So 1, it matches a point, but you have to know that the point is not the point of 0. That is this question. So that I misunderstood. It is important, but then I know that S half is far away from the 0 because 0 is at 0, 0 is at half. Okay. So now the thing is, this is there. So if I repeat and repeat, I get that u at 1 by 2 to the k, ball of size 1 to the k, because S1 is normalized to 1, grows like 1 minus delta k, 1 by 2 to the k. Now this is like r, and this gives me an extra r to the alpha. And this alpha is exactly log 2 of 1 by 1 minus delta. Right? So if delta is very close to 1, it is 0, but because delta is little bit bigger than 0, this is a number bigger than 1, so log 2 of that is positive. Right? So how much this cone opens up? So this means that u is C1 alpha at this point, which I have normalized it to the tangent plane, which is 0, because I have sort of normalized situation that u minus l, so that u is above xn equals to 0. I subtract out the affine part. So now, and then I know by the semi-continuity properties that Devabrata was mentioning, here the tangent slopes cannot vary too much, because if it does, okay, if it is too bad, then it has to either cross here or here, right? And then in that case, it sort of violates the fact that the graph is convex, okay? So therefore, and I know the other thing that all these AH, because from the other side, what do you have? I also did the other thing. S half is, you have to stay away from this, right? S half, you have to stay away from this. So in general, if you repeat this, you also get that S of H is less than or equal to ball of H to the mu. Because at in half the set, half the region has to step away from the boundary. So if I slice my section at smaller and smaller scale, there is a H to the mu that comes because of this 1 minus delta on the other side. Right? Because at every time I have a geometric sort of a dilation of the size 1 when I rescale. So therefore, not only do I know these transformations which normalize the section, so what did I have? So what is it that I'm trying to say? That one has to look at now is 430, but let me continue because I think this is too exciting to stop, right? So this is like, I've cut a section, and now is it clear? This gives you C1 alpha, right? The cone of monotonicity. So I don't do anything more. Because if then it tells me that the slopes doesn't change much. So around each of these points, I can cut a section and I can get a universal C1 alpha estimate all throughout. And let me just make this point more. So what I do is that I make it, normalize it to B1 and this, okay? So that this minimum point is more or less like the center, and this affine map, this determinant of AH is like H to the n by 2. And not only this, because of the fact that you have to slice it, at every H, okay? if you iterate it, because S1 is like 1, so therefore what you get is that any AH that you do, when you repeat this, the size norm of AH is no more than h to the mu. Which is to say that S of H or S of H is contained in BH mu. So that you really lower, right? You are really getting closer. And so therefore, in a SH region, okay, which is contained in BH mu, and because of the C1 alpha regularity, in any SH region, the slopes cannot change more than, or slopes cannot change more than H mu to the alpha. H mu because you get, because SH and BH need not be comparable, but they are comparable up to a power. But whatever power is the positive power, but inside that you have that these are like the slopes can only vary like h mu to the alpha. So therefore, if you take a section little bit here and at a bigger height, it engulfs the section at the origin, right? So this is the engulfing property of the section. Let me not describe that. So this is the C1 alpha, and now what else? So now let me tell you the C2 alpha. Okay, so this is the C1 alpha property. So in the Debye-Process context, it tells you that once you have that the linear map is Alexandrov, okay, solution, and the right hand side is just bounded away from 0 and that, then the phi that he had as a solution, it is C1 alpha, so the transport map is C alpha. So now let me upgrade it to C2 alpha, okay. But this is like a small perturbation theory because the real geometry is in this other one, okay. So this is more like if I have det of p square u equals to 1. So I did not even do anything about the Pogelerov's estimate, which I feel very bad, where I have that. And now what I do is that by taking a small enough sections and normalizing, okay, I would know that how this transformation acts. This acts like f of AH, right? And this has norm like h to the mu. So therefore, if I have f of AH of x as f tilde, I know that if f is C alpha norm is bounded, then this can be made as small as I want. So I can say that f minus 1 is less than equal to a small delta times mod x to the alpha. And this delta I will change, okay? And now what I do is that if this happens, so this is all coming from the other, this is coming from the Alexandrov's estimate, iteration of the Alexandrov's estimate. And now what I do is that once I normalize this, okay, by taking a small enough h, because all the smaller sections are not very widely behaved, that is what the universal strict convexity character tells you. Now I want to get better information that the separation from the tangent plane is quadratic plus 2 plus alpha, okay? So now what do I do? Well, this is what it is. So I have a situation where det of d square u equals to 1 and f minus 1 separates like delta mod x to the alpha, right? Well, det of d square equals to f. Now what I do is that I solve for w, det of d square w equals to 1, and this is all in the normalized picture S1, okay? I've deduced it by taking a small enough h. And then that of these, and then you do w equals to u equals to 0 on the boundary of S1. 1, 0 doesn't matter, okay? So now the thing is that, what do you know? By the Alexandrov's estimate, right? These two differs by a very little. So f minus 1 in the first case is less than equal to delta, right? So therefore, by taking 1 plus delta times w or w by 1 plus delta, you can get very close to the Monge Ampere measure of this without affecting the boundary values, right? So therefore, you get that w minus, so you will be able to trap. So therefore, you will be able to trap by 1 plus delta w, and from below by 1 minus w by 1 plus delta, right? But delta is like this, depending on del delta by something which I don't want to quantify. All in all, what I have is that u minus w is controlled by delta. But then the thing is that I know that because it's controlled by delta and the section is normalized, so at 0, this is far away from the boundary, right? The section is normalized and this is far away from the boundary. And so, and because u and w are very close, so w of 0, w at 0 is far away from this boundary values, right? So at w, I can apply the Pogelerov's estimate, okay? So I'm just using the fact that 0 is far away from the boundary because the section is normalized to size 1. So 0 has to be far inside because this is not really B1, it is S1. So there is a B1 inside and there is this. But because I know that this size is 1, so by Alexandrov's estimate, this 0 has to be located far inside. Okay? And therefore, I know that for W, I can use the Pogolarov's estimate here, right? This I solve by the Caffarelli-Nirenberg-Sprague theorem. And for this W that I have, I can use the Pogolarov's estimate. So W minus P exists and is less than equal to some C times R cube, right? A quadratic polynomial, which by an affine transformation, okay, I can make it like 1 by 2 mod x square, right? By an affine change. If it's an ellipsoid, I sort of change the axis a little bit, but because by the Pogolarov's estimate, I have a third derivative control, right? Because Pogolarov's gives you C2, from C2 you can upgrade to C infinity. So I have everything that is good inside, okay? And then what I know is that U minus W, because it is trapped in this manner, is less than equal to constant times delta. Okay, so therefore U minus P, the rescaled one. So this is in BR. So if I rescale this, this would behave like C delta R minus 2, right? In the BR region, which I make it B1. So I just take U minus P R of X by R square. So that is why this comes, and the CR cube gives me a C of R. Okay. And now you know how to choose this quantity and then finally normalize the picture. So what you do is that you first make, in order to make this whole thing less than epsilon, okay, less than some desirable quantity, less than some epsilon naught, what you do is that you first choose R very small so that this is like less than epsilon naught by 2, and then you choose delta small enough compared to this R, okay, so that this whole thing is also again epsilon naught by 2. Okay. Clear? And that I can always do because if I sort of keep on taking smaller and smaller sections, I can curtail the oscillation a lot because oscillation of this is less than equal to the oscillation of F times h to the mu alpha because of the fact that these norms are less than h to the mu. So there is a decrement, right? It's not exactly h to the alpha, but h to the mu alpha because that is what the Alexandrov's estimate gives me. So this is what you have. So therefore, I can have a normalized picture now where I will have the following assumptions that I will have that after this reduction, I have that there is a d at d square u equals to f such that f minus 1 is less than equal to delta naught epsilon naught mod x to the alpha, and I have that u minus p is less than equal to epsilon naught. This is something that I have to repeat. So now I have a situation that at the scale 1, I am close to a polynomial, and at this point I can apply the Savin's small perturbation result, which says that if I have a flat solution to a fully nonlinear equation, then I don't need the concavity, I get smoothness. And this is exactly that, except for the fact that because it's the Monge Ampere, I need to, I just want to do this step more explicitly because I never did the Savin's flatness result. Okay, so there is a lot of theory that is all coming in over here. Okay, so let me do this step more explicitly. Okay, so now my claim is that there exists delta naught, epsilon naught, and R naught that I will choose such that there exists polynomials pk, okay, which will be like ak plus lkx plus qk x comma x. So let me call this part qk, pk or pk x comma x. Let me call it pk because I call that the p, such that u minus pk over br is less than equal to epsilon naught r to the power 2 plus alpha, but the alpha is the same as the f alpha, where r equals to r naught to the power k. That is that every dyadic scale, this r naught will be my dyadic scale, such that below that I have this much. I have done it at scale 1, right? That is the normalized situation I have at scale 1. So now I repeat. So suppose I have done it up to scale k. Suppose I have done it up to scale k. Suppose it is done up to scale k as Hirsch did in his compactness arguments. I will repeat. So suppose done up to scale k. And then what I do is that from this I isolate this linear part. Let me call it Lk. Okay. Okay. So what I do is that I take R naught of k to be my r, because I don't want to write r naught to the k and all the time. Okay, so I just write this to be now my w or v, because I want to compare it with w, which is u minus just the linear part, but not the quadratic part. Okay, u minus this Lk of Rx by R square. And because I know at this scale the separation happens like this, and this the pk part, this is pk, this is pk. So let me call it qk. Okay, because this separation happens, and I already isolated up to the first order part, and the second order part is invariant with respect to the scaling, quadratic scaling. What I get is that v minus this pk is less than equal to epsilon to the r plus r to the alpha, where r is r naught to the k, but this epsilon is related to the previous epsilon by another r to the alpha. This is epsilon naught r to the alpha, right? So this is one qualitative good information that I have. And now for this delta of d square v, what I do is the following. And not only that, I have that this closeness is there. And what I have, and in all of this, what I want to do is that delta of d square of pk equals to 1, because eventually you expect this to go to the quadratic approximation at 0, and delta of d square u at f of 0 is 1, right? F of 0 is 1. That is what my first estimate is, right? Is a small oscillation in this Helder norm near 1. So what I do is the following: v is there, this is there, and then I take a solution to Monge Ampere of this rescaled one, delta of d square w equals to 1, okay, and w equals to v on del v1 for the rescaled one, okay. So then the thing is that because again I know that d square w, delta of d square w is 1, and f minus 1 goes like delta naught r to the 2 plus alpha, the delta naught epsilon naught r to the alpha, right? This is how it goes. So therefore, this immediately tells me that this is how it goes, right? So for this, let me see. Yes, I think it's correct. Yeah, this is how it goes, right? Because so epsilon naught r to the alpha is like epsilon. Okay, delta naught times epsilon. Okay, because I want to retain the epsilon, because epsilon naught then I will relate at the very end. Okay, so then once this is there, f minus 1 is less than equal to delta naught epsilon. Okay, and then what do you do? Then I know that w and v cannot be that far, right? So w minus v is like constant times delta naught epsilon. Okay, clear? And then what do I know? I know that v minus pk is very close, so w minus pk is also very close. And the difference of two solutions to a fully nonlinear equation satisfies the linear elliptic equation. Because if you remember, f of d square u equals to f of d square w, d square v equals to 0. This u and this v are different v. Okay. Then what I do is that I can just write it as d by dt of f of t d square u plus 1 minus t d square v 0 to 1 is equal to 0. And when you expand this, you get this del f by del ij, which for the current Monge Ampere operator is still surviving. Why? Because I am in the cone of positivity, right? Far away from this, because all these polynomials are not only this, they are bounded. All these qk's are bounded, and I will show that these quadratic part has to separate like r to the alpha, the linear part has to separate like r to the 1 plus alpha, and the 0 part has to separate like r to the 2 plus alpha. Okay? So therefore, you see, like when you expand this, you get the difference. You get that this is del f del ij of this whole thing inside v minus u ij. Okay, it's a linear one. So therefore, what I have is that w minus p solves a nice linear elliptic PD. So what is w minus p? So w minus p would then be, if you combine this and this, okay, if you combine, okay. No, I think I have exaggerated. So this is epsilon, okay? Where epsilon is epsilon not r to the alpha. There is no like r to the 2 alpha, okay? So there is a repetition. This is less than equal to epsilon, where epsilon is epsilon not r to the alpha, right? Because this is the only missing piece. Because I could have divided by r to the alpha again, but since I retained the quadratic scaling, so there is only one r to the alpha that is going up, right? So it's not like r to the alpha times r. So this is too much. So w minus p will be less than equal to v minus pk. V minus pk plus w minus v, right? W minus v plus v minus pk is w minus pk, and that is that is what? So P minus P, W minus Pk is less than equal to constant times epsilon, right? Because it's W minus V plus V minus Pk, right? Right? So this is there. So this is what I have qualitatively for this. Again, I will update this, okay, based on this. So now the thing is that this is in a good set, B1. And I can therefore use my Kovalev's estimate to this thing. And I would know that because this is small, therefore, in half the set, B1 by 2, this is less than equal to, and here I can take the C21 norm. This is less than equal to C epsilon times C times epsilon, right? So therefore, there exists some P tilde. So there exists a P tilde, which is the quadratic approximation of this, such that W minus Pk minus this P tilde is less than equal to C epsilon R cube. And now what I do is that I take the difference, okay? So now what I do is that I need to go back to my V, okay? So V minus this Pk minus P tilde will be less than equal to V minus W plus W minus Pk minus P tilde that I have at scale K. Maybe I should denote it by K because this P tilde changes from scale to scale, but I think the context is clear. So what I have is that therefore V minus Pk minus P tilde, which will be my Pk plus 1 eventually, is less than equal to C. So this is C delta naught epsilon, and this is plus C of epsilon R cube, right? So therefore, what I can do is that I can move this certain terms inside. I can take epsilon inside. I can move C delta naught plus R cube. Okay. So then what I again do is that I want to make this small, right? I want to make this like R to the 2 plus alpha. Okay. So wait. This is strange. Something is strange. So what do we know about this? So that this is less than equal to, I divide by R square. So this is less than equal to this. So V minus Pk minus P tilde in this region, in a certain BR region, right? In a certain BR region is less than equal to that. So now, so this will be now done in some R naught, okay? This will be decided. So this I do in my R naught region. So this is not R region because R is used there. So this I think in the rescale picture over here should be done over a R naught region, which is what I need to find, right? This needs to be done in the R naught region because then this R naught I will relate to the other one, okay? So then therefore this is R naught cube. Now what I do is that I make this to be R naught to the, because 2 plus alpha by 2, because alpha is strictly less than 1. So this goes to 0 faster than R to the 2 alpha by 2. And then I choose my delta naught depending on this alpha and R naught. So that this entire thing is less than equal to epsilon naught times R naught 2 plus alpha. And then when I go back to my original picture, okay, this would be then in terms of U, because this part doesn't change. This is only the quadratic part, right? Up to some, again, this also has a linear part, but let's ignore it for now, okay? Because it scales the right way. But then if I just look at the quadratic part, this would be like U minus Pk tilde. This would then be in the size, in the next scale, which is like R naught. This was already R naught, so that becomes R naught to the K plus 1 would be less than equal to R squared, which is like R squared means R naught to the K 2K, and then there was an epsilon. Epsilon is R naught to the K alpha, right? Because it's R naught to the alpha with an epsilon naught, and then there is additional R naught to the 2 plus alpha. So this is less than equal to epsilon naught R naught to the 2K plus 1 alpha. Wait, 2 R naught to the K plus 1 2 plus alpha, right? So 2K plus K alpha plus 2 plus alpha is 2K, K plus 1 2 plus alpha. This is because this is R naught to the K plus 1. So and then how do these polynomials change? These polynomials change in the following way, right? because this P tilde, because I have bound on the C21 norm by epsilon, so this D square of P tilde will be at most like C epsilon. But this is like, so this is let's say the quadratic part, epsilon is what? Epsilon naught to the RK alpha, and which is like epsilon naught to the R alpha, right? And which is like R naught K alpha. So that means that when I do these processes, Pk minus, so the Pk minus Pk plus 1, which is the quadratic part, has to separate like R naught to the K alpha. Likewise, because I happily cheated on the linear part that may come from P tilde, when I rescale back, what does it become? When I rescale back, it simply becomes R naught to the 2K and this linear part AK, okay, AK and plus LK X, right? Means not AK, means some A tilde and LK of X by R naught square, R naught 2K. But now this part, because on R naught by K, because X by R naught K is R, right? Because the linear part then becomes in the that one is Rx, that was X, but when I go back to X, this becomes X by RK. So the AK part differs by R naught to the K and with A tilde, and that is epsilon, that is another R naught to the K alpha, because R to the alpha. So the linear part, so the A naught part, AK minus AK plus 1, also varies like R naught to the K plus K1 plus alpha, right? And well, R naught to the 2K1 plus alpha, right? 2K plus 1 plus alpha. And then the linear part, R naught to the K2 plus alpha, 2 plus alpha. And the LK minus LK plus 1 varies like R naught to the K1 plus alpha. So they geometrically decrease, okay? And you get the limiting one, that Hirsch did, where you have a C2 alpha estimate at the origin, right? Clear? So this is the small perturbation theory that gives you, and therefore you see that how you apply in the context of the Minkowski's problem. Of course, I didn't do the Komodorov's estimate. So let me just roughly give you an idea what that is, okay? So if you have delta of d square W equals to 1, W equals to 1, okay, and W equals to 0 on the boundary, or U. I just cannot do it because it's going to exceed too much time and this is already very heavy. So roughly the idea is based on the Bernstein's technique. And you can find a good account of that in the book of Gilbert-Frudinger. So this is not very difficult to understand, okay, Bernstein's technique. So what you want to do is that you want to measurize U11, okay, in one of the directions, okay, pure second derivative. So what you do is that this you multiply with, you cut off at the boundary, so the maximum is before the boundary, so you multiply it with minus U, and then you add in the Bernstein's technique a convex factor, which in this case is e to the square, okay, and this you call as W. And then what you do is that you look at where max of W is obtained. So then you want to see where the min of W, right? Min of W is obtained. Okay? Because min of W will be a bound on U11. Sorry, max of W. Because you have taken minus U. Max of W is attained. So at the max of W, you will have that Wi will be 0. And if you have U, so you will have that at that point, what you can do is that you can assume that the whole system is diagonal, okay? Clear? You can diagonalize the system because if you apply to a directional derivative, then along that coordinates you sort of diagonalize, okay? So you just assume that Ui is diagonal. So you will also have that Ui, Wii will be less than or equal to 0. Okay, this is one information that you use. You will also use that. Since Ui and since the direction is 1, U1 equals to 0. This is one direction that you will use because this comes from derivating delta of d square U equals to 1 at the maximum point. Okay. Well, at the maximum point, because it satisfies the equation, this is what you will have because these are classical solutions with Kokolorov. And then when you derivate it again, you get this quadratic part with a negative sign, which then becomes so Ui. One will be derivating this, which will give you U11ii. But then you know that when you take the derivative of this, you have to differentiate this, okay? And that comes with a negative sign. So this essentially is if you do d by d epsilon squared and epsilon equals to 0 of the trace of a of a trace of A inverse of B, okay, what you get is minus of B. So A plus epsilon B inverse of B, okay. When you do this, twice derivate this, because that is what you are doing here, right? You want to derivate this along the U11, okay, and then you will apply the chain rule. So this is nothing but minus of trace of A inverse B, A inverse B, that gives you the quadratic form. And if you assume that at that point where the maximum is attained, it is a diagonal structure. So you apply essentially to begin with UEE, and at the point of maximum, you make it the one of the principal directions, okay, where it sort of diagonalizes. And therefore, this is minus of this. If you put it to the other side, when you do it with a diagonal structure, this B will be like U1 ij, because you have derivated it inside, U1, because you have already derivated this once inside, and this one will be like UII, and this is like UJJ, right? And this is kind of the trace, right? Because this B is then derivated with respect to one which has already appeared. So this on the right hand side, after you will see UII, UJJ of U of 1 ij is square. So, and the other thing that you will use is that U of II, UII equals N. So if you put all this information together, what you will get is that this quantity, when you put all this information together, you will get at the point of maximum, U times U11 is less than equal to something, okay? And then, if you go to an interior point, U has to be sufficiently below, because if you go to an interior point over here, then you can always find a paraboloid, okay, that doesn't cross the boundary. So this point is far below. So this will give you a bound on U from below, which will give me a bound on U11. But there is a computation that is involved. So I think I underestimated the fact that I could do all of that in this. So this is one thing, and 5 more minutes. So let me just tell you another thing, which is something in the global lens. With this C2 alpha estimate, as I see, we can finish the Minkowski's problem, right? First, you will upgrade to C1 alpha. That will give you that the gradu is C alpha, and then it will give all the way up to C infinity. And then first you will then, for the Minkowski's problem, original Minkowski's problem, that will then, therefore the theory will apply to strictly convex points. And then again, you can apply the theory to extremal points, where you can cut this section. And now, if on the surface there is a flat part, you trace this flat part till you reach an extremal point, and here you can cut a section where this is below, because the surface rounds up. There you can get the strict convexity, and that will contradict the fact that you started from the flat portion of the boundary and trace all the way up to here, because here the surface has to curve. Okay, so you cannot join it by an affine segment. So this is there, and now something in the spirit of fragment Lindelof theorem, which is the Calabi's theorem, that global solutions are quadratic polynomials. So Calabi, and with this I will end. Okay, I mean I regret that I could not do that estimate, but at this moment, this is a very nice estimate to do. One should do it. Okay, so in the book of Figali, you will find this to be for general as this that. You require FPC too, okay, because you have to derivate this whole thing twice, but just do it for one, because that is what we require in Caffarelli's proof of C2 alpha, right?
So basically at the maximum point it is less or equals to 0, so trace that term is less or equals to 0, and from there you are getting the estimate. So what is the role of W? I didn't understand.
No, the role of W is because when you do this, okay, essentially what you do is that you take again the log of this so that you can isolate this.
So basically the same idea. You take the log and the
Yeah. So finally, you don't apply to this. I'm just pretending it because I want to show that this is the same as the Bernstein's technique. Okay. But in practice, when you do it in a way, and at the extremum point, you get that U times U11 is bounded.
That comes of this trace
Yes.
equals.
Yes, and because this quantity is bounded, up and down, because I have a good understanding of the gradient, because U is 0 there and delta V square is something, right? And by barriers, I can bound the gradient and convexity, and therefore I get a bound on U1 on the whole set. And now if I go step inside the domain, U has to decrease enough. We have seen similar ideas before, and therefore U is strictly minus U is like comparable to 1. And in such sets, I get a bound on U11.
Right hand side is constant. That is very important. I mean,
yes, and in the book, this is for C2. So because you need
for C2, okay, then you can do it.
But then the thing is that I wanted to do it for 1, because to recover the Popolarov's estimate, I can go via the Caffarelli's theory. First, I will get C2 alpha, then I can keep upgrading. So in the very first step, because when Pogolorov did it, Caffarelli C2 alpha theory was not there. And you see that it is important because you have to pass as an intermediate step from C1 alpha to C2 alpha. So in order to apply it to the, what is it called? In order to apply it to the original problem, okay, Minkowski's problem, you require to go through that passage. You cannot go right away to C2 alpha. So this is one thing. So now let me tell you Calabi's theorem. It tells me that if I have det of d square of u equals to 1, which again will use what Devoprata did, okay, is in Rn, then u after an affine transformation is like 1 by 2 mod x square. Okay, in general it's just like a quadratic polynomial, but after an affine transformation it is that. Now, if I have a global solution, it has to be strictly convex, which is something that is an element that Devoprata also used, because otherwise, if it is linear on a line, okay, if it's affine on a line, that line has to exceed the domain, but the domain is at infinity. So I can, after an again affine change, I can assume that u of t 0, 0, 0 is 0. So which is this line, right, along the E1 axis. But then, as Devoprata said, right, then because of convexity, because if I have a point here where the slope is pointing here or here, and then if I the slope is pointing here, at this point, if I tilt the graph too much to come here, I will go above u0. And likewise, if the slope is here, if I tilt the graph here, then I will again exceed the graph of u. So, and I know that for a convex function that cannot happen because the entire thing is to be. So these are all Alexandrov solution, okay? So for a convex thing, this cannot happen. So you cannot be equal on a line, okay? So it's strictly convex. And now I will tell you that then the idea is that the same thing that I did for the fragment Lindelof principle, that uniqueness of positive harmonic function that vanishes on the boundary of the cone. Now my claim is that all the sections look alike with the eccentricity. Because if I have, this is like height h, this is sh, and this is say height 1, s1. Now, if this is very distorted, okay, if this is very distorted, if I normalize this picture to, so suppose this is like this distorted, very badly distorted, and this is like round at the height s1, then when I normalize this picture, this I will stretch to, and then this becomes a ball. But in that process, when I stretch this, I also end up stretching this, the one at s1 which was already rounded, so that becomes like this. And then therefore in the coming back picture, okay, what I see is that this lives at 1 by h level, this is at h level, and then if something is rounded at some scale, at all below scales, it is C2 alpha, it is universal weight. And then this eccentricity being bad in this direction tells me that the C2 alpha norm will be very large, and that cannot be. So therefore, whether I go at, so for a global problem, whether I am at infinity or 0, they are the same, because I can always go down, right? Or blow down. So when I start looking at h, make it 1, everything looks universally round. So and this s1 then becomes at a level 1 by h. Because of the universal C2 alpha estimate, what I will have that d square of u of s1 in the room, when I look it from the rescaled picture at size 8, I can make, and because then this will be at 1 by h, and because of universal C2 alpha estimate, d square of u minus u of 0, d square of u of 0 in S1 can be made like epsilon if I take h to be large, right? Because all the eccentricities I know are kind of like uniformly bounded. Otherwise, I will have this explanation then. This also goes the other way. If this was distorted and this was good, when I come back, again I will violate the universal C2 alpha estimate that I have established for my normalized solution. Normalized means at some scale I can't, and at all scales below, things are better. Okay? And now this does not, let me tell you, this does not violate the Pogolov's example, because the Pogolov's example that I had, I solved an ODE, and that ODE stops in a certain ball in the xn direction. So I cannot continue far away. Okay? So therefore, this is less than epsilon. And now if I take h going to infinity, I get that the d square u are all the same. But there is nothing special about 1. I can do it for S2, S3, S4 as long as h is far away. And so therefore, by unique continuation, this has to be the same one, because this has to be the same quadratic polynomial all throughout, right? So therefore, this tells me that, so this is exactly the same argument that you do for the fragment Lindelof. So this is another big arsenal that Caffarelli brought in. You look from infinity, or you look from close, zoom in or zoom out, they are the same for the global problem as soon as you have the scale invariance, okay? So this is roughly the Caffarelli theory. There is a lot more. that I wanted to cover, but let me stop over here. Okay. That is all. So now Harish will